Hello and welcome to my presentation about robustness in computer vision. First of all, I want to talk about what is actually robustness in vision models. So vision models are deployed into autonomous driving applications, medical imaging and security functions, and they must work under unpredictable conditions and unpredictable kind of noise. These models should also generalize really well, not just generalize. By generalizing, I mean they should not only work on the training set and validation set, but also in the real world. Talking about the real world, I've got a little short story about a company, Swiss company, called Logitech. Most of us know it probably because we have one of their computer mouses, keyboard, or any webcam of that. So a professor of mine back home in Switzerland, he was actually working in the CTO office of Logitech, and he was a lead vision engineer. And they realized there's a big discrepancy between theory and practice. So in theory, like all of these ImageNet dataset problems, they were kind of solved because all the models had like great accuracy, way above 90 something percent. But as soon as they used their own images from the real world, which they took with their Logitech webcam, all of their model failed. So there's definitely like an out of distribution error that can be observed. Another thing that is super important is security and trust. So adversarial robustness protects against manipulated inputs meant to fool computer vision systems. And last but not least, I want to address the scientific integrity, so that a robust computer vision model should be fair, interpretable, and should produce reproducible results across datasets. Now going back to the 80s, I want to talk about where computer vision started and what the challenges were. So there were basically handling variability in the data. So there are three methods that I want to introduce real quick. One is called the Huff transformation, which is used to detect shapes like lines and circles in noisy images. Then there's the random sampling, random sample consensus, RANSAC method, which is a robust estimation method to handle outliers in feature matching. And then there's the well-known SIFT, so scale invariant feature transform, and the histogram-oriented gradients, which are basically feature descriptors robust to rotation, scale, and lighting changes. One project that I did in the past, around 2017, I had the opportunity to develop an eye surgery device, which you can see in the top left corner. So there's basically a camera in there which is pointing towards the eye of a patient, and the camera sees the eye. Now we need to track the eye, so the pupil. To do this, we apply the Huff transformation on this noisy image. We transform the circles, circles in the image space, into the parameterized Huff transformation space to find the center of the circles and also the radius of the circle. And as soon as we found those parameters, we transform them back, overlay them with the original image, and you see the eye with the outline of the actual iris. That's actually what we want to see and what we want to track. And this device won a Red Dot Design Award in 2018. Going a little bit forward into the 2010s, deep learning entered the stage. So we all know deep models, they have an amazing performance, but they also introduced a new robustness, or introduced new robustness challenges. So for example, in 2014, they realized that if you implement or if you add tiny perturbations to fool the model, it will misclassify some examples, and these are called the adversarial examples. On top of that, there are dataset biases. So since deep models are feature extraction models and they learn their features instead of relying on handcrafted features, if there's a bias in the dataset, the model will also learn that dataset. Designed by its nature because it's a data-driven approach. and then there are certain architectures, for example CNNs, so convolutional neural network, which rely on texture rather than shape, leading to poor generalization. It's just a inherent nature of the architecture itself that needs to be addressed. We've seen problems on the one hand side, because now researchers had the problem. They had like models which were performing really, really well, but they have huge robustness problems. So researchers did what they are able to do best, which is identify problems. So for the adversarial examples, they realized, okay, if they add tiny perturbations, I can fool the model. So why not add tiny perturbations during the training of the model already to improve the robustness of the model? And that's what they did just 1 year later, which is called the adversarial training. Another robustness improvement from my point of view is the defensive distillation, which was invented in 2016. The idea here is that a data-driven model basically can have an arbitrarily crazy decision boundary or non-smooth decision boundary, and defensive distillation actually smooths out this decision boundary to reduce the sensitivity to adversarial noise. Last but not least on this slide, there's the certified robustness, which is a really, really nice robustness technique from my point of view. So what they do is they actually have an input, add some noise, and do that a couple of times with the same input, add noise, run it, add noise, run it, add noise, run it, and they average it out. And after they average it out, they can compute the distribution and can guarantee mathematically that the model will be robust to some degree against some degree of perturbations. Next big topic, which arose around 2010-2020, so in these 10 years, is the domain adaptation and generalization topic. So beyond adversarial robustness, researchers tackled domain shifts, where training and test data come from different distributions. So what they did is they came up with a method called the domain adversarial neural networks, so the DANCE in 2015. The idea is to learn domain invariant features via adversarial learning. So what they do, we have the same structure as usual, which starts with some input X. We have described in green here a feature extractor, and then we have the label predictor, which is kind of the classification layers. And now they added in pink domain classifier, which actually identifies the domains of your training data, which can come from different domains, and they average it out based on the domain, basically. So they correct the features for domain-specific features, resulting that the feature extractor will learn domain invariant features via adversarial learning. In 2020, they did some advantages in data augmentation, so they introduced mix-ups, dilation, and synthetic to real adaptation to improve generalization, which basically means they added different textures and different colors and all that kind of stuff to the images. They flipped and rotated it. They used simulations. That's what synthetic to real adaptation means. They used simulation to come up with all kind of crazy data augmentation they can do. Last but not least, test time adaptation, invented in 2021, where the model is adapted on the fly using entropy minimization. So this means there are certain processes, for example, back in the day I was working on injection molding machines, which are mass producing plastic pieces. And so due to changes in temperature, time of the day, humidity, and all that kind of stuff, you can have drifts in all kind of measurements. And so there are models which need to adapt to this kind of drift. And the test time adaptation is one of these models which is able to do that and is still state of the art at the moment. And it uses entropy minimization. So basically, at every moment in time, it computes the entropy of the predictions, and it monitors them, and it also corrects it. Exactly. Yeah. Basically, what it updates the model's batch normalization parameters, and it minimizes the entropy on its predictions. That's how it works. And as I said, TENT remains a milestone method for online model adaptation on the Shift until this day. Now, my favorite part of the whole survey that I did was the out-of-distribution detection, because it's one thing that a model is desirable to should work in all kind of situations, and most probably that's not always true. It works under certain assumptions defined by the characteristic and properties of the training data set. But the out-of-distribution detection is a thing where you can say the model realizes that it sees data which is out of distribution. It has not been trained on, it's not confident in the prediction, and that's a super powerful thing. That basically started in 2016 with the maximum softmax probability, which is basically a simple threshold based on confidence scores. So the model is predicting something, and it's not just doing the max, the highest activated class. It looks at the distribution, and it needs to pass some threshold, otherwise the model says, I'm not sure, I'm not giving any prediction. After that, in 2018, researchers came up with the Mahalanobis distance, that's a really difficult word, which is basically measuring the distance in the feature space to detect anomalies. And the distance, the Mahalanobis distance, is measured in units of the standard deviation. And last but not least, there are energy-based models which basically use the energy to improve the out-of-distribution detection. And the energy is an input, so that's the negative log sum of exponentiated logits, which correlates with the unnormalized log likelihood of the model's output distribution. And the researchers were able to show that the energy scores yield a cleaner separation between the in-distribution and the out-of-distribution samples compared to the usual softmax probabilities, which are most often too overconfident. In the last couple of years, there was a rise of large-scale models. For sure, one of the most famous one was released in 2021 by OpenAI. It's called CLIP, so Contrastive Language Image Pre-training Model, which is trained on massive 400 million image and text pairs, improving the zero-shot robustness like never seen before. Next to that, there's a method called Dino, which is a self-supervised method, which is called distillation with no labels, applied to vision transformers. The authors found that when a vision transformer is trained with self-distillation, which is basically a student network trained to match a momentum updated teacher network's output, the learned embedding have remarkable robustness and structure. Notably, a Dyna-trained vision transformer automatically segments objects in images. The attention maps of the vision transformer act as segmentation masks, and though the model was never trained with segmentation labels, it's still able to output segmentation masks. And last but not least, there's the general thing which is well known in right now, which is robust retaining, which basically formalized the situation that scaling up models on diverse datasets improves the robustness across multiple domains. Of course, the dataset needs to fulfill certain requirements. It needs to be diverse, you need to be debiased, you need to be kind of balanced, etc., etc., etc. There are many nuances, but they show that basically the performance scales with size of the dataset in general. Then there's another super interesting topic from my point of view, which is certified robustness at scale. Where is it? Certified robustness at scale. So the randomized smoothing, which was invented in 2019 and still is in place today, so kind of one of the state-of-the-art method, which guarantees robustness against small perturbations. So what it basically does is randomized smoothing converts any classifier into a smooth classifier by averaging its prediction over noise-added versions of the output. And last but not least on this slide, provable defenses for transformers, which was invented in 2024, extending certification techniques to large vision language models. So basically, the author proposed a method to certify vision transformers by imposing a Lipschitz bound. And a Lipschitz bound is basically a restriction on how much a function is allowed to change from one step to the next one. So basically they're also smoothing the function, which is a common idea in robustness, as we learned throughout this talk. Now, talking about, we started in the 80s, we came to the 2000s, then to the 2010s where deep learning entered the arena, and then we looked at the state of the art, what happened in robustness in the last couple of years, and now I want to talk about the future, because this is something that I'm working on as well right now. So on the left hand side you can see like the previous state of the art and like one of the go-to tools to understand an image computer vision model, which is gradient class activation maps, GradCams. So basically they use the gradients from the last couple of layers and they feed it back into the feature maps, and then they look at the feature maps using a heat map, which tells you where the model was looking at. But sometimes it's not that's not enough information, because it could be looking at the texture, it could look at the shape, or something else on that object. And it doesn't matter if you use a grad class activation map or Shapley class activation map. By the way, Lloyd Shapley, he won a Nobel Prize in economics for his Shapley values, which basically tells if you've got a group of people and they complete the project and you remove one, you look like how much the performance of the project dropped. Then you remove the second person and you look only the second person, then only the third person, only the fourth person, like each and every contributor one by one, and you look how much the performance drops, and depending on the drop in performance you can say like how much that person contributed to the success of the project. So he won a Nobel Prize for that, which was super nice, but not really applicable to economics, but in machine learning and computer vision it's tremendous tool, because we can rerun experiments with a different set of features all the time, and so you can do that as well. So here Shap class activation maps basically shows how much did one individual pixel contribute to the actual decision. But again, we have in grad class activation maps and in Shapley class activation maps, we look at pixel spaces and we have to interpret ourselves what the model is seeing. On the other hand, what we wish on the right hand side is that we can ask it with human language. So basically the next best thing we have are text prompts, that we can ask our model what it's doing. So we came up with an idea to use the basic overall clip architecture based on the green image encoder and the purple text encoder from OpenAI, and we came up with an idea how to integrate information from your standalone computer vision model, depicted in red, the red image encoder, and transfer information on how your red standalone image encoder is working into the image encoder of CLIP, and then use the text prompts to kind of assess and to understand, using text prompts, what your standalone image encoder is actually doing. So, as a wrap up, we started in the 80s, gone to 2000, 2010, and now we looked at state-of-the-art and of the future about robustness in computer vision. So, of course, handcrafted features in the beginning, then learned features after, and tools called explainable AI that we can apply even in the deep neural network era. So for the future, things that I think, due to my research and the survey that I did, which are super interesting in the next couple of years, are especially multimodal robustness. So we want to ensure that models can integrate vision, language, and sensor data robustly to improve generalization and security. Then there's adaptive robustness, developing models that dynamically adjust their architecture and training strategy based on the deployment conditions. Then there's the one thing which applies to neural networks only, so neural network verification, advancing formal methods to provide strong guarantees on model behavior and robustness to adversarial perturbations. And then again, 2 points which are also applicable to traditional computer vision methods: causal robustness, so infusing causal reasoning into vision models to help them distinguish between spurious correlations and essential object feature. This would be one of the most interesting things. And last but not least, human-in-the-loop systems, leveraging human feedback to improve robustness, uncertainty estimation, and out-of-distribution detection in real-time application. From my point of view, that's one of the most interesting and most important things. So we can say that robustness in computer vision has evolved from handcrafted feature engineering to adversarial defenses and large-scale self-supervised learning. The future lies in combining these strengths to create truly generalizable, trustworthy, and resilient computer vision models. Thank you for your attention.